Hi, hello everyone. My name is Avinash Jairam. I'm a doctoral candidate at the City University of New York Graduate Center. I'm also an instructor at Medgar College of the same university system. Today, I want to talk to you about how we prove who we are on our cell phones, our smartphones. How do we authenticate ourselves? And I want to demonstrate why the current way we do it is failing us. So mobile shopping has hit $2.5 trillion last year. At the same time, 85% of organizations say mobile attacks are rising, and 78% of people reuse the same password across various accounts. Now, here's the problem. Uh, a password is a single point of failure. Once it is stolen, once it is compromised, it gives an attacker, an adversary, a hacker, unlimited access to your device. So what we need instead is a continuous, invisible authentication mechanism, something that works in the background of your mobile phone and cannot be stolen. So this is what my research is about. It's about developing an algorithm that runs in the background of your smartphone while you're using it. Uh, an algorithm that does not interrupt your use of the phone, uh, that provides convenience and security at the same time. So, how am I going about building this algorithm? Uh, I'm using an alternative mechanism called behavioral biometrics. So instead of asking who you are at a single moment, it asks whether the way you're using the device right now matches how you always use it. So your touch patterns, the way in which your fingers interact with your smartphone screen, how hard you press, how fast you swipe, are as unique as your handwriting. And your touch patterns are shaped by years of muscle memory. So this table that I have here shows the key advantage. A password is easily stolen. A password can be easily stolen. A fingerprint is checked once. However, a behavioral biometric is extremely hard to forge and works continuously the entire time that you are using the device. So, how it works? 5 steps. The sensors in your smartphone screen record every single tap, such as the pressure that your finger is exerting on the screen, the position on your screen relative to the device, the duration, how long did your finger rest on the screen. It does this 100 times every single second. So the sensors are collecting data 100 times per second. This data gets summarized into numbers, uh, where a mathematical model or a machine learning model can learn from. So during early use, like imagine when you get your smartphone, you're unboxing it, you're setting it up. Uh, the system builds a profile of what your behavior normally looks like. So you can build a mathematical function based on a user's finger patterns. Thereafter, every interaction is quietly scored against that profile. So if your score drops below a certain threshold, the phone asks for confirmation, such as it may ask you to uh, re-enter your PIN, for example, or check your Face ID again. So the key point here at the bottom is if you are the legitimate user, right, you would never notice any of this because your finger patterns would match that of what's saved on the profile. Hence, this system will be completely invisible. So, how has the research evolved? A quick history. Early work got 85 to 92% accuracy, but models that are trained on Monday may reject you on Friday. Why is that? Well, our behavior changes. Uh, on Monday, we may be full of energy. By Friday, we might get tired and our behavior would change. So, deep learning, this is a subset of machine learning, has pushed accuracy above 95%. And combining touch with motion sensors made the systems even stronger. But here's a critical finding. Even the best models degrade in real use over time. Your behavior drifts. So, for example, someone during the week may get injured, right? Or under a lot of stress. The way in which you touch your phone, if you're more anxious, right? I mean, your touch patterns can vary. So, a frozen model, right? A model that was trained 6 months ago may not recognize you today. So this phenomenon is called behavioral drift, and it's a central unsolved problem in this domain. And this is exactly what my research addresses. So one term we need that's very much relevant to my research, a baseline metric, is the equal error rate, the EER. It's the point where the system wrongly accepts imposters at the same rate it wrongly rejects the real users. So a lower equal error rate is better. So a 5% equal error rate means 5 in 100 imposters will slip through the system. So this chart tells the story. Uh, a frozen model, a model that's never updated, reaches 31% under real drift. Now, an adaptive system, a model that is constantly evolving, an evolutionary model, can get below 5%. And this is what my model, my work, my research is targeting. So, open challenges, to be honest about why this is not deployed everywhere as yet. Drift remains the hardest problem. Privacy is also a real concern. Continuous data collection raises questions about who owns your behavioral profile. So, who owns your biometric data? Is it you or is it some third party? So, cross device portability is imperfect. So, a model may identify you on one device, let's say your iPhone, but if you go to your iPad, it may not. And user acceptance matters. If the system rejects you too often, you will turn it off and not be too inclined to use it again. So security that is too aggressive defeats its own purpose. So this is my contribution. Can we build a model that adapts in real time as behavior drifts, without storing the history and without retraining from scratch? So I'm using the HMark dataset. This is a benchmark dataset in my field. It has 99 users and it collects data. It collected data from in 24 sessions each, touch and motion sensor data. I trained my model on the first 3 sessions and test on the fourth session to simulate real use over time. So the algorithm that I'm utilizing is called real-time recurrent learning, RTRL. It updates the model one gesture window at a time on the device with no stored history. The model adapts continuously as you use your phone. So the result, a model that is frozen, that does not evolve, that reaches a 31% equal error rate under drift. My adaptive model reaches 9%, a threefold improvement. And because real-time recurrent learning uses constant memory, it can actually run on a mobile device. So it is designed for deployment, not just for running in a lab. So what does this mean for organizations? For developers and providers, the technology works. Uh, you can pilot it on high-value transactions, build it as a layer on top of existing authentication, and establish data governance policies now before regulators force you to do so. For researchers and educators, behavioral drift is real use. Uh, Behavioral drift in real use is the most urgent problem in this field. And for all of us, Digital security literacy is no longer just an IT concern. It's a business competency. So all around the world, more and more business is done on mobile devices. So for example, at a farmer's market, you would see many vendors are using electronic tablets or various types of kiosks to process mobile transactions. So in conclusion, um, to close, passwords are broken. Behavioral biometrics offer a continuous, invisible alternative. The barrier, however, is drift over time, not raw accuracy. And adaptive learning closes that gap. And authentication architecture is a strategic asset. Uh, Liability and customer trust depends on getting it right. All right, this brings me to the end of my presentation. My citations are on this slide. I am happy to share the paper, the data set with anyone that is interested.
Yeah,
Thank you,
thank you.
and I greatly appreciate the opportunity to
Yeah,
present.
thank you very much.